So the main point is the concept of bus. So what actually is a bus in a power system? As you have seen in your electrical circuits course, that the points in the electrical circuits where there is an interconnection or a point where there are two or more elements are connected, it is called as a node. In the same way, in the power system, technically a node is called as a bus. So a bus is just a node at which two or more elements of the power system are connected. And these elements in the power system, as you all know, they may be generators, transformers, transmission lines, and what else? There are different new types of components in the power system. So any two or more of these elements, if they are connected, and that particular point is called as bus in the power system. And it is not necessary that all of these elements should be connected at every bus. It is just two or more elements. It is then enough for a connection at a bus. And a bus is basically indicated by a thick line, whether it is a horizontal or most of the times it will be vertical. But it can be sometimes horizontal also. It is indicated by a thick line at which number of components are connected. You can easily identify that. I'll show you. So this is a single line diagram. If you carefully see, there are four end users and there are two generators, if you can see in the figure. These thick lines, if you can see, these thick lines are considered to be the points where you are having interconnections with two or more elements. And these thick points are called as the buses. See how many buses? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So 12 buses are there in this power system. So it is called as a 12 bus power system. And see, if let us suppose if I designate this particular one as bus number 1, see what are the elements it is having? It is being connected to a generator transformer connection, and it is having two transmission lines which are being connected to two different buses. Similarly, if I take this one, it is having a connection to the end user and it is having two transmission lines which are connected to some other points in the power system. So like that. A bus is nothing but an interjunction, what we call it as, in a power system. Now moving ahead. Buses are basically characterized in our load flow studies by two important variables, or what we call it as four quantities. The two variables are, the first one is the voltage, the second one is the power. Since these two are considered to be complex variables, we are supposed to consider them as four individual variables. The voltage magnitude, the voltage angle, the complex power magnitude and the complex power angle. Now, when you do have four things, the voltage magnitude and the voltage angle and the power magnitude and the power angle. Now these two, power magnitude and the power angle, they can be converted into your what I call rectangular coordinates. And if you consider the rectangular coordinates of the complex power, these are considered as P and Q, which is nothing but our active power and reactive power. So literally speaking now, I am redefining the voltage magnitude and the voltage phase angle, and these two are the active power and the reactive power, and those are being mentioned there on the slide. So every bus is characterized by four quantities: voltage magnitude, voltage angle, and active power and reactive power. In a load flow study, particularly, out of these four quantities, only two quantities will be specified, and the other two you are supposed to determine. Depending upon the variables which are available at that particular bus, the bus gets its name. Now, I'll show you. This is a sample power system where you can see there are 5 buses and there are 2 generators, and we assume that these arrow marks are represented as a loads. Now, how many loads are there? 4 loads are there, 2 generators are there, and totally 5 buses are there, assuming that this is a sample power system. Now, coming to the bus classification. you leave this slack bus, we will be primarily concentrating on only two buses. One is a load bus and the other one is a generator bus. So how do you determine whether a bus is a load bus or generator bus? Just by seeing the single line diagram. It's very simple. If a generator is connected to a particular bus, it is called as a generator bus. And if a generator is not connected, it is considered to be a load bus. See once again. If a generator is connected, it is called as a generator bus. If a generator is not connected, it is to be considered as a load bus. Don't get to a false impression that if a generator is connected, it is a generator bus. If load is connected, if it is a load bus. No, nothing like that. If generator is connected, it is considered as a generator bus. If generator is not connected, it is to be considered as a load bus. Now, I'll show you. In the smart system, see there are two generators which are connected to bus number 1 and bus number 5. See at bus number 5, apart from the generator, there is a load also. But since it is connected to a generator, bus number 5 will be treated as a generator bus. And bus number 1 will be treated as also a generator bus. So the remaining 2, 3, 4 buses will be considered as a load buses. So from the single line diagram, we can come to a conclusion that if a generator is connected, it is considered to be a generator bus. And if a generator is not connected, it is called to be a load bus. Now the question is, what variables? All the variables will be specified at all the buses, but only we will be considering only a particular variables, that those are going to be a standard ones. The remaining variables can fluctuate. So which variables are considered to be standard at any bus? See, as I have already told you, each bus is characterized by 4 variables: voltage magnitude, voltage angle, and active power and reactive power. Out of these 4, which are to be considered as standard at each of the buses. Now, at generator bus, a generator person, let us suppose if I am a person in charge of a generator, I will be more concerned about maintaining my voltage magnitude. So my primary concern will be voltage magnitude, and the second one will be the active power which I am able to generate. So that's why a generator bus, at a generator bus, if there is an availability of capital P and mod V, what we call it as active power and voltage magnitude, these two are considered to be the standard options, standard variables, which means that the other two, they can fluctuate. So at generator bus, the standard variables are P and mod V, magnitude of V. Whereas at load bus, if let us suppose I am a consumer, I am not concerned about the voltage. It is a duty of the people, it is a duty of the government, it is a duty of the entity. They will take care of the voltage. I am more concerned about what is the active power I am getting, what is the reactive power I am getting. So that's why a load bus is basically characterized by 2 standard variables called as active power and the reactive power, P and Q. Once again, generator bus is characterized by P and mag V, whereas load bus is characterized by P and Q. Now I will show you. The first one is load bus, or what we call it as a PQ bus, because the standard variables are P and Q. So at bus at which the active power and reactive power are specified, it is called as a load bus. And what are the 2 parameters which we are supposed to determine here? Mag V and delta. These types of buses are very most common, and they do comprise of somewhere around 80 to 90% of the buses in the given power system. Most of the buses are load buses. And the next one is a generator bus, at which a generator is being connected. Since the standard variables are P and mag V, it is sometimes called as a PV bus. So the reactive power Q and delta are to be determined through the load flow equations or load flow solutions. Sometimes in some textbooks it is also considered to be as voltage controlled bus. And these type of buses, they do comprise of somewhere around 10 to 20% of all the buses in the power system. Now, whenever we are doing a load flow study, as I have already stated, the primary constraint is about power generation is equal to demand plus losses. So our major concern is we are supposed to satisfy that particular constraint, but doing this one is a tedious task. So that's why what we will start is, we'll start with the generation is equal to demand, and then we will include the losses at the last. So if we start with the generation is equal to demand, and if we complete all the solution and finally we equate the generation is equal to demand, now the question arises, where are the losses? So that's why what we do is nothing but we will keep one generator aside and treat it as a separate one, and we assume that it is going to supply the losses. Now I'll make it very clear to you. Now I do have a 100 bus power system, and I do have 20 generators which are catering to my, let us suppose, 80 load buses, let us assume. Now these 20 generators, let us suppose if the generation, the positive power injections is equal to the negative power injections of these load buses. Now this is the demand and this is the generation. Now generation is equal to demand. Now nobody has considered the losses. So where does the losses come from? So that's why what I am doing is I'll keep a generator bus aside. Now my generator buses are 90 and I do have 80 load buses. These 19 positive power injections are equated to my 80 negative injections. So generation is equal to log found with the demand. Now plus losses. These losses are being covered by an extra generator which is capable of generating my power. So in this way load flow studies is being carried out. So of all the generators, one bus is kept aside and it will be treated and it will be kept aside in order to cater the losses of your system. It is just an assumption. So now, one.